good evening. Welcome to another episode, and today we will be discussing the fundamental theorem of arithmetic. Okay, so before we get into that, let's discuss something else. Let's begin with the definition of prime numbers and composite numbers. So, take any number that So before we get into that, let's look at something else, prime numbers and composite numbers. So take any number that you know. Let's take, for example, 10, right? And one thing that is quite apparent is that 10 can be written as the product of 2 and 5, and 5 can be written as the product of 5 and 1, right? So the general idea is that any number is either a prime number or it is a composite number. So what I mean by that is that any number that you can think of, either it can be further divided or it cannot be divided, in which case it can be divided by 1, but that is quite trivial because every number can be divisible by 1. Alright, let's now move on to the fundamental theorem of arithmetic and what it tells us. Okay, so this is the statement of the fundamental theorem of arithmetic, which states that any natural number, in our case for example 10, can be written as the product of prime numbers. So in the case of 10 we have 2 times 5. And moreover, this representation is unique up to a reordering. So by reordering I mean just change the order of where the prime numbers are. So 10 can also be written as 5 into 2, or 20 can be written as 5 into 4, 5 into 2 into 2, or it can be written as 2 into 2 into 5. And each of these representations are unique. Alright, so now let's begin the formal proof of the fundamental theorem of arithmetic. Okay, so let's take this proof case by case. So the first case is that n is in fact a prime number, in which case we can just write n as n and we will have the required representation. So that is quite trivial. But now let's move on to the second case. So case 2, where n is not a prime number. So that means that n is a composite number. So n can be written in the form a, b, where a and b now since n is a composite number, it can be divided, and therefore it must have a smallest divisor. So let's call that smallest divisor d. Let's call it p instead of d. So since p divides n, we can write n as p times n1, and my claim is that p is a prime number. Why is that the case? Because p is the smallest possible divisor of n, and because of that it must be a prime number, because if it weren't, then that would mean that p could be further broken down into a and b, which would contradict the fact that p is the smallest divisor of n. So we have that p is now a prime number, and n can be written in the form p1 times n1. And we will now do the same trick but for n. So for n1 we have that n1 is either a prime number or n1 is not a prime number. So if n1 is a prime number, then we can just write n equal to p1 times p2, and we have the required representation Or the second case is that then that n1 is not a prime number, which means it is a composite number, and by virtue of being a composite number, it can be rewritten in the form p2 times n2, where p2 is the smallest possible divisor. And now we have the same representation but in the following form. So we have n is equal to p1 times p2 times n2, and we will perform the same trick on n2. So if n2 is prime, then we have n is equal to p1 times p2 times p3. But if n2 is not prime, it can be further broken down into a smallest divisor, and eventually this process is going to terminate because we have that n2 is less than n1, which is less than n. And we know that this sequence of numbers is bounded between 1 and n, so eventually it will terminate, and we will find a representation of n in the form as desired. Now we need to show that this representation is in fact unique. So in order to prove that this is a unique representation, I will first begin by proving a lemma which states that if P divides AB and P does not divide A, then it must be the case that P divides B. And let's move on to the proof. So we have that P does not divide A. So that means that the GCD of P and A is equal to 1. And that means that we can write P times X plus A times Y equal to 1, which is a basic fact from arithmetic. But now notice that we can just multiply this expression by B, and we will get B times Px plus Ay is equal to B, which can be written as Bpx plus Bay is equal to B. And we have that P divides AB, and we have that P divides this expression over here, because we can just factor P out from here. So we have P divides Bpx, which is in fact equal to B. So from there we can conclude that P divides B. We need to now show that this in fact is a unique representation, and we will do that by way of contradiction. So assume it were the case that this were not a unique representation, then we would have that n is equal to P1, P2, P3 all the way up till Pk is equal to Q1, Q2, Q3 all the way up till Ql, where all the P's and all the L's are distinct. So let's now pick a particular P from this set, Pm, let's call it. And we know that we can rewrite this thing now as Pm times C. Basically we take Pm and we multiply all of the other numbers with themselves, and we get that that is equal to Q1, Q2 all the way up till Ql. But that would imply that Pm divides Q1 up till Ql. But by our earlier lemma, we know now that there exists some Q, let's call it Qn, such that Pm divides Qn. But that would mean that Qn can be written in the form Pm times some constant c. But since Qn is itself a prime number, we know that the only representation of Qn is equal to Qn times 1, which implies that Pm must be equal to Qn. And by a similar argument, we can show that every element of this set is equal to some arbitrary element of this set, and by doing that we will have then shown that these two sets are equal and this representation is unique, right? So that concludes the proof, and if you enjoyed it, please do leave a comment or let me know what you think. Thanks for watching.